Let f be the function defined by f of x equals square root of the absolute value of x minus 2 for all x. Which of the following statements is true? So we have this function f of x, which is the square root of an absolute value. If we were to graph this function, it would look something like this, where one of these, where the graph is symmetrical across the line x equals 2 on the left and right hand side, and on each side of x equals 2, we see the curve make this kind of a shape, which looks like your normal x minus 2 square root graph of a square root of x. And the other side is just the reflected version of that. So we see both of those graphs because of the square roots here. Because either the negative or the positive value of x doesn't matter, because when we take the square root, it only considers the positive value. So the answer choices all look at the point x equals 2 here. So let's go through them one by one to see which ones are true. So A says f is continuous but not differentiable at x equals 2. So to determine whether something is continuous, all we need to be able to do is be able to draw the curve without lifting our pencil. So as you can see, there's no holes and there's no jumps in this graph. So that means that this entire graph is continuous. So that means that x equals 2, it's also continuous because the left and right hand limits both approach the same point as we get closer to x equals 2. So we're continuous at x equals 2, but the graph is not differentiable at x equals 2 because graphs are not differentiable at points where there's a corner. So a corner is any sharp turn in a graph. So like if we had a graph look like this V, this looks like an absolute value graph, or any cusp. A cusp is similar to a corner, but it doesn't necessarily the curve doesn't need to be straight. As long as there is a sharp turn, a function is not differentiable. The reason is because as we approach the corner here, we see that the slopes of these lines is constant here, and it's this constant negative value. But then suddenly, at this point, the slope seems to change because going from the right-hand side, the slopes are this constant value that is positive. So since there's this, you could say, discontinuity in the slopes of the left and right-hand side of the corner, the point is not differentiable. Because we can't use the left, because the definition of differentiability uses limits from the left and right-hand side. And since the limits of the slopes of the left and right-hand sides do not approach the same number, it is not differentiable at the corner. And the same reason for the cusps. The cusps have different slopes approaching from the left and right-hand sides. If we were to draw tangents on this graph with a different color, so if we were to draw tangents, we would see that the tangents approach this sort of vertical slope from the left-hand side, and they're all negative, and the ones on the right-hand side are all positive. So, but once we get to this point here, we see that the left and right-hand slopes disagree. So that means that at corners and cusps, graphs are not differentiable. So A seems to be true. We are continuous at the cusp here, but not differentiable. B says f is differentiable at x equals 2. This is false. We have a cusp here, so we are not differentiable. So B is false. F is not continuous at x equals 2. This is false because we are continuous. We can draw through from the left of x equals 2 to the right without lifting our pencil, meaning the limits of the graph from the left and the right-hand side, are both approaching the same number. In this case, a y value of 0 at x equals 2. The limit as x approaches 2 of f of x does not equal 0. This is false as well, because from the left, we see the graph is approaching f of x equals 0, and from the right, it is also approaching f of x equals 0. X of x equals 2 would be discontinuous if there was a jump, meaning there was, say, a hole at this graph. Like if this part didn't exist, and instead there was a hole where there was a completely other graph like this, meaning the left hand limit would approach a y value of 0, but the right hand limit would approach a different y value. But in this graph, we see that the left and right hand side both approach a y value of 0, since they're going towards the x-axis. X equals 2 is a vertical asymptote of the graph of f. No, because the graph passes through this. If there was an asymptote, the graph would be passing through it, and the graph would exist at the asymptote. The value of the graph here at an x value of 2 is a y value of 0. So the point 2, 0 does exist on the graph. So this cannot be an asymptote. So the correct answer is A.